We know that this itself is just another abstraction or another modeling. Now that we understand the behavior of this NP junction, we want to make another abstraction, make another modeling, go one level higher. So we model this behavior or everything that we talked about as follows. We say we have the PN junction, the P, the majority carrier are holes. In the N-type, the majority are electrons, and we have something that we call the depletion region, which has been created because of the diffusion current. Since we have more electrons in the N-type, they move to the P-type. Since we have more holes in the P-type than N-type, we have the movement of holes in the electrons as in the N-type as well. Or in other words, since electrons are more in the N-type than the P-type, they move to the P-type, therefore leaving positive ions or leave the N-type a bit more positive. We model that by saying that we have a depletion region or an electric field, that we said how electric field would oppose the diffusion current. Now imagine that we want to connect this to a battery. Let me actually, so let's say that we connect the P-type to the negative side of the battery and the N-type to its positive side. Obviously, you would expect that the electrons would be attracted to the positive side of the battery, and holes would be attracted to the negative side of the battery. So this is the movements of the holes, and this is the movements of the electrons. We also know that electrons move in the opposite direction of the electric field. So if electron is in direction, the movement of electrons, this has to be the created E field caused by this battery in here. And as you see, holes in here are moving in the direction of the electric field. So you see another electric field has been, by putting this battery, an electric field has been created in this direction. So right now, this depletion region would be increased. And the reason is that since electrons are leaving the N-type, therefore they would make the N-type would become more positive. And since holes are also leaving the P-type, therefore the P-type is losing positive charges, and therefore it would be a bit more negative. So the length of this depletion region is going higher. We could just now model this as this image in here. We have a bigger electric field in between. So we say this type of connecting the NP junction or the PN junction to the battery as the reverse bias. So if the previous case, when we didn't connect it to any battery, we said it was equilibrium because the current resulted in from the electric field equates the diffusion current, and therefore you wouldn't have any current, and that was the equilibrium. In this case, we say it is in the reverse bias. As you see, we don't have any movement in between. Electrons move in this direction and holes move in this direction, canceling the electric field, we could in a way say. So what we mean is that, and therefore we said it leaves an N-type a bit more positive and P-type a bit more negative, but we wouldn't have any current in between. Now you might say, since electrons move in the opposite direction of the E field, we have some electrons, the minority carrier in the E field, that would move in the opposite direction of the E field in the N-type. And also we have a bit some holes as the minority carrier in the N-type, that they would move in the direction of the E field. And therefore they both contribute to a bit of current in the depletion region as well. See, we call this depletion region. Well, that's right, but because it has been caused because of the minority carrier, and we have obviously their number, their amount is smaller than by a huge amount. So we say the current that is resulted by this minority carrier is small, even though sometimes we just ignore it, but we just show it by I of S. So we say right now we have bias or PN junction, or in the reverse bias, we have connected it to a battery whose the P side is connected to its negative part, and the N type is obviously connected to the positive side. Also, as the last note for this lecture, I wanted to mention that if you look at this PN junction, you see that we have a side in here that charges could move freely. We have a side in here that charges could also move freely. Just forget about these wires for now. And we have something in between that charges cannot move, ignoring that I of S. So it acts as an insulator. We explain if you have two plates that charges could move with an insulator in between, that is a capacitor. So by increasing this battery, we are saying that the value of this battery, since the depletion region is getting increased, and since the capacitance of a capacitor is equal to epsilon A over D, this is the equation for that. We explained a bit about its relation with A and D. Since the distance between the two plates is increasing, so we say the capacitance is decreasing, meaning by going more reverse, I guess, in the reverse bias region, by increasing this value of the battery in the way that is connected, by increasing its value, the depletion region is getting bigger and bigger, and therefore the capacitance of, therefore we could just, well, in a way we could just say PN junction acts as a capacitor, so we say the capacitance of this capacitor is decreasing.